Hello, chemistry students. So this is our first lesson in the last unit on electrochemistry. So in this introduction to electrochemistry, I'm going to go over some important concepts and terms that you'll need for the rest of the unit. So let's get started. Okay, now you may have heard the terms, words oxidation. You also may have heard reduction. Oxidation you may have thought means combining with oxygen or reacting with oxygen. And although that's not entirely, it's not wrong, it isn't, of course, the entire story. And reduction would then mean removing oxygen, right? So we're going to get more into the nitty-gritty of this and figure out what these exactly mean. Maybe this says modern here, but maybe we'll just say the more accurate definition will be described. We will go over right now, and that involves the transfer of electrons or the movement of electrons. Okay, so let's basically define this, and then we'll look at some examples. So oxidation essentially means the loss of electrons. Okay, so when an element or substance loses electrons, it's said to be oxidized. And reduction then means gaining of electrons. And there's a couple ways to remember this. Now, the way that I was taught, that kind of stuck with me, is this one. This mnemonic device is Leo the lion says grr. So losing electrons is oxidation, gaining electrons is reduction. So Leo the lion says grr. Another way I've heard of is oil rig oxidation involves losing, reduction involves gaining, and that refers to electrons. Okay, so a couple of mnemonic devices here for you to remember the definition of oxidation and reduction as it pertains to the movement of electrons. Okay, so we will look at an example. Now, whenever an oxidation and reduction happens, something has to lose and something has to gain. These work hand in hand, right? So this involves both, meaning we're going to condense this term now, oxidation reduction reaction, into what it's commonly referred to as a redox reaction. So we're going to look at this example here, and this is solid zinc we're combining with a solution of copper 2 sulfate, producing a single displacement reaction, copper solid and zinc sulfate. Okay, so the easiest way to define or to figure out what is losing and gaining electrons is if you write the net ionic equation, because here you can see what those charges are. Okay, so let's look at this. Solid zinc here has a 0 charge, right? Solid zinc, no charge. Now this copper ion has a positive 2 charge, sulfate has a minus 2. Now in our product side, we have solid copper this time, and that has a 0 charge. Zinc has a plus 2, and sulfate has a minus 2. So then we see how have these changed. Zinc has gone from a 0 charge to a positive 2 charge. Okay, so let's focus on zinc first. So zinc has gone from a 0 charge to a 2 plus or a plus 2 charge. Now we know that electrons carry, now this is the part that can sometimes get a little bit confusing, but electrons they carry a negative 1 charge. So did zinc lose or gain, essentially, is the answer, or rather is the question. Did it lose or gain electrons? So did zinc become more positive or did it become more negative? So here it looks like it would have lost electrons because it became more positive. Electrons would have left zinc. So if zinc is going to become more positive by losing electrons and gaining a more positive charge, we know that Leo the lion says grr, and losing electrons means oxidation. So zinc would have oxidized. It would have gone from a 0 to a positive 2 charge. Okay. Now I'll reveal this more in just a bit. Now copper went from a positive 2 charge, so copper here went from a positive 2 charge to a 0 charge. That's for copper, 0 charge. So here, looks like for it to become more negative, look, it's gone from positive 2 to 0. For it to have become more negative, it would have had to have gained electrons. Okay, so we saw that zinc lost. So we write that down here. Zinc lost electrons. And here it looks like copper has gained, right? It's gained electrons. Now, how many it has gained, how many each of these have gained, they should be equal. Now, they are not always equal. We'll get into balancing our redox reactions in our next lesson, but here we see that zinc has lost 2 electrons, and here we see that copper has gained 2 electrons. That's perfect. So our net ionic equation then looks like this. So zinc will lose 2 electrons in this reaction, and copper would have gained those 2 electrons. So 2 out and 2 in. Perfectly balanced in terms of charges here, and this is a redox reaction where we can now define that there is an oxidation reaction happening between or among the zinc, solid zinc to zinc ion, and then along here there is a reduction reaction happening here. Okay, now we can split these reactions up. We can look at just what's happening to zinc, even though these are happening at the same time. We know they are, right? Happening at the same time. We can split these reactions up into what are called half reactions. So we can define this portion of the reaction as the oxidation reaction, and this portion here as the reduction reaction. Again, oxidation means, again, zinc going from 0 to positive 2. So we're losing electrons here, gaining electrons here, oxidation, reduction. That's how we're defining that. Now, a couple of more terms. Okay, so zinc is considered to be, here is zinc, it's in the oxidation reaction, but it's considered to be the reducing agent. It is what causes the reduction of copper. Yes, zinc is being oxidized, but it's what causes the reduction of copper. Similarly, copper, right here at our reduction half reaction, copper, yes, it's being reduced, but it is the oxidizing agent. It is what's causing the oxidation reaction here to happen. Okay, so another way to look at it is zinc, yes, zinc is part of the oxidation reaction, it's losing electrons, but it's gaining, or rather it's forcing copper to gain, causing the reduction to happen. And copper, yes, it's part of the reduction reaction. It is gaining electrons. See how it gained it on the reactions end? It's gaining electrons, but it's forced zinc to give up those electrons, if you want to think of it that way, causing zinc to oxidize. So copper is your oxidizing agent. Okay, again, these happen simultaneously. They happen together in these reactions, even though we split them up into half reactions. So just again, a reducing agent, right? The reducing agent causes the oxidation reaction to happen, right? An oxidizing agent causes the reduction reaction to happen. Now, oxidation states, you've probably heard of this since grade 9, and it's been called a few different things. You may have heard valence charge, or you simply may have heard of, or it may have been called just simply charge, or oxidation number, right? A few different terms for this, but essentially it means is what is the charge? If it were an ion, what would the charge be, right? So nitrogen, if you look at a periodic table, nitrogen can have different charges. Depending, and now that we know a bit more about the quantum model of the atom, nitrogen can have different charges. It can have a +5, a +4, +2, or it can gain or lose 3 electrons because of where it is in the periodic table. So it won't always have that most common +5 charge. It may have other charges. So simply looking at a periodic table won't tell us what charge it has. Although those are the most common charges, it can have others. So we're going to then figure out what those charges are. Okay. In this case, here we have solid sodium, 0 charge, diatomic bromine, a 0 charge for oxidation numbers. Now, if we look at their new charges now as sodium bromide, well, sodium has a +1 charge and bromide has a -1 charge. So it's gone from sodium has gone from a 0 charge to a +1. Okay, so that means, again, Leo the lion says grr. Okay, so it's gone from a 0 to a +1. It's lost electrons, so it's oxidation. Now, if we look at bromine, bromine has gone from a 0 to a -1. It's gained electrons, therefore it's reduction. Okay, so what we're doing here is we've looked at these oxidation numbers, And these oxidation numbers then allow us to define if an oxidation or a reduction reaction is happening. So it's important to figure out what those oxidation numbers are. There's a few tips here we'll go over. These are actually best summarized here. Okay, I don't usually read over how-to rules or tips on how to steps on how to perform a reaction or a process, but these are important to briefly go over. So column 1 and 2 typically have these charges. Okay, they will have a column 1 and 2 in your periodic table. These families, your alkaline earth metals, will have a +1, +2 charge. Okay, so along those columns we'll have +1, +2. Hydrogen can at times be confusing, but it will only ever be a positive or a -1. We know that hydrogen's electron can be lost, right, or it can gain an electron to be isoelectric with neon. And this is a great one to remember. Oxygen will always be -2. So if you see oxygen written, it's always -2. Okay, elements in their natural state. So for example, back to that example over here, sodium, solid sodium is 0. Diatomic molecules, remember Hoffer-Nickel, those are also 0. So when in doubt, it's usually 0. Look at their natural states or check to make sure they're in their natural state or not. Okay, then the sum of all their charges are equal to 0. Now, let's say there's no charge on, remember this from our organic chemistry unit. This is ethane, so there's no charge here. See, there's no charge, no number there. It's just not there. Okay, so if we're going to figure out what our oxidation numbers are, for example, they would have to equal 0. Now, if we look at something else, if we look at, let's say, sulfate, SO4 2- or -2, then all of the oxidation numbers here between sulfur and the 4 oxygens, they would have to add up to give you a total charge of -2. So in the case where the sum should be 0, well, then all of the sum of all of the oxidation numbers should be 0. But if it's a polyatomic, or if it's an ion, then it should add to equal that specific charge, that indicated charge. Okay, it helps to look at examples to put into context, so here's a couple of them. Okay, so this is dichromate. Dichromate has a total charge of -2. Now, what makes this portion with oxygen is easy is that you just define it as a -2 charge. Now, this tells us that there are 7 oxygens at a -2 charge, so 7 times -2. There are also 2 chromium atoms, 2 of them. We don't know what the charge is on chromium, but there's 2 of them. Now all of that, if we add all this together, so I put a plus sign here, if we add all that together, it should equal a total of -2, because it's indicated here that it has an overall -2 charge. So look what we've inadvertently done is we've created a linear equation, right, back to grade 9. So 2 chromiums plus, this is going to be -14, is equal to -2. A little bit of grade 9 algebra. Okay, we're going to bring this over to the other side. What we do to one side, we do to the other. So plus 14 here eliminates this, so we have to add 14 there as well. We get 12, and we get 2 chromiums. Divide each side by 2, and we get chromium has a +6 charge. So now we successfully completed the assigning of oxidation numbers to each of these elements. Chromium is a +6, and oxygen is a -2. Just to check your work, if you'd like, you can take +6, multiply that by 2, and add that to -2 times 7, and you should get the charge as -2. So now we've assigned oxidation numbers, and we're done with A. Now, this is copper 2 nitrate, see, because nitrate we know to be a polyatomic. So if you recall, nitrate is a polyatomic, but this polyatomic ion is within this ionic bond here. So let's start assigning charges, but first let's deal with this nitrate. Okay, so we're going to deal with nitrate first. Maybe I'll choose a different color for that. Let's deal with nitrate. So nitrate we know has a -1 charge. We also know that oxygen is always -2. So let's work on that linear equation again. So we know that it has to equal a total of, it has to equal a total of -1. Okay, so -1 minus, and we have 3 oxygens each at a -2, so there's 3 times -2, and there's 1 There's just one nitrogen. So let's simplify this now. We get that. Turns out nitrogen is a positive 5. So good, we have nitrogen at positive 5. We know that oxygen is -2, and we're over half done. Now we have to just figure out what the charge on copper is. Now intuitively, you can look at this and say, well, we know that nitrate is -2, so copper has to be, sorry, nitrate is actually -1, but because there's two of them, nitrate contributes a total of -2, so copper has to be +2. Now you can show your work here. You won't need to, but you can show your work and you can say nitrate, there's just one copper, right? There's two nitrates. There's two nitrates right here. And we know that nitrate each has a -1 charge. And does it have an overall charge here at all? Any number, any ionic charge here? No, there is not. So it has to be 0. So what we get is copper -2, 0. Copper is then +2, right? So you can show the math here, but you can also just look at the known polyatomic charge and determine that copper is +2. Okay, so we've now assigned oxidation numbers to each of these elements. Right, another example here of how these oxidation numbers help us determine the flow of electrons. So similarly, similar to one of our first examples, zinc has a 0 charge. Zinc has a 0 charge, and it's gone from 0 to, let's see, so here nitrate in total has a -1, well, individually has a -1 charge, but there's two of them, so zinc has to be +2, right? We know from our last example that nitrogen in nitrate is +5 and oxygen is -2. Okay, so that's all done. Okay, so here we have nitrate. Nitrate has a -1 charge, okay, like that. We know that this is -2, this is +5, just from our last example. Again, I will go back. That looks like something else. Okay, +5. Okay, go back. I said that nitrate has a -1 charge. Now that allows us then, as a polyatomic, allows us to determine that silver has a +1, and I'm trying to fix this so that it all fits in nicely, but this is, nitrogen is +5. Okay, this is a -1, that means silver has to be a +1. Okay, so here silver exists in its natural state, solid silver, so it is 0. So assigning these oxidation numbers will then allow us to figure out that zinc is our reducing agent. In other words, it's losing electrons. In this case, it's lost 2. It's lost electrons, it's oxidized, right? League of the Lion says grr. Therefore, it is the reducing agent. Now, silver here has gone from +1 to 0, so it's actually gained 1 electron. That makes it the reduction reaction, so this is being reduced, which makes it the opposite then, an oxidizing agent, therefore causing the oxidation reaction to happen here. Okay, notice, unlike our other example, the number of electrons lost doesn't appear at the moment to equal the number of electrons gained. Now, yes, it does have to do with, look, coefficients here, right? This is just a bit of a clue, a little bit of a preview of what we're going to do next. Okay, at the moment it does not appear to be balanced. It is. We'll talk more about this in more detail later. Here is your reading from your textbook and questions. Post any so that I can answer. I hope this helps.